In today's lecture, we are going to discuss a very unusual event which occurred about 600 million years ago. This is called the snowball Earth. That is the time at which the entire Earth was covered with ice. Now, this was not realized till recently. If you recall, we had mentioned in the very first lecture that Earth's climate has oscillated between ice-free conditions and ice-covered conditions during the past billion years. But the actual evidence that this has happened was obtained only recently. Now, you must remember that the fact that Earth's climate had oscillated can be obtained from very simple energy balance model. If you recall, we discussed this very early in this course, that if you balance the energy coming in, that is energy absorbed from the sun by the Earth atmosphere system, and the energy radiated to space, in steady state the two are in equilibrium, the emission and the absorption. The black line is absorption, dotted is emission. And we see that there are three possible solutions. That is because the absorption curve is complicated, is shaped like an S curve. Okay? That is because if the Earth's global mean temperature is very low, then the entire Earth is covered with ice. Well, if it is almost ice free like today, it will be around 15 degrees centigrade or 288 degrees Kelvin. And if it was like the last ice age 20,000 years ago, it will be somewhat cooler and partly ice covered. So, the amount of ice covering the surface of the Earth determines the Earth's albedo or reflectivity. So, because of the unusual variation of the absorption of radiation, this black line is S shaped, while the emission is somewhat simple curve, and they intersect at 3 points for the present incoming solar radiation. Okay. So, we had already discussed a lot about these two, even the present climate and its variation, and what happened in the last ice age. Okay. We did not discuss this possibility much because till recently we were not sure whether this actually occurred in the past history of the Earth. Okay. The person who first derived this equation in 1969, Mikhail Bediako, assumed that if Earth was covered with ice, there would have been no life on Earth, hence such solution is not possible in the real world. But he was proved wrong. Okay. So, most people thought if you have ice covered Earth, no photosynthesis is possible. So, life as we know it, which depends on photosynthesis, would not be there, okay, after this event. But the discovery that indeed there are evidence from proxy evidence showing that Earth was indeed covered with ice completely changed the whole picture. Okay. Now, why are people worried? Because as the thickness of ice that is covering the Earth goes on increasing, the amount of photosynthetic available radiation PAR goes on decreasing, and if it goes below a certain limit, photosynthesis is not possible. So, people felt that ice of the thickness of 20 meters or above ever existed all around the Earth, then life could not have survived. So, that was the basis of the assumption that snowball Earth could not have occurred. But proxy data on global mean temperature shows there was a period around 500 million years ago when the temperature of the Earth was sufficiently low that snowball Earth could have occurred. Okay. This is worth of casting at all. And when people were looking at evidence, they saw two periods, the Marino one between 635 and 655 million years ago, and Turitian 660 to 750 million years ago, when rocks which were unearthed in these parts on Earth, they were found to be having evidence of glacier. Not only that, these rocks which are now there at very high altitude like Canada and parts of Europe and Australia, these rocks were not at this place, they were near the equator. So, how do you know that? That is based on paleomagnetism. Okay? When rocks form on Earth, that is, they solidify from a molten lava, they essentially freeze the orientation of the particles, the magnetic orientation, with reference to the place where they became solid rocks. Okay? So, these rocks which were around the equator 600 million years ago, they are now much farther away, but because we can find the paleomagnetic evidence, we can argue that these rocks are actually, when they were formed, they were actually near the equator. So, paleomagnetism depends on the fact that there are magnetic lines of force on Earth because of the molten lava is made of iron and it is circulating, and so if the rock is formed on the North Pole, then the orientation of the magnetism will be vertical, okay? Either North Pole or South Pole. If it is formed around the equator, it will be horizontal orientation. Okay? So, this amazing technique will tell us where the rock was when it was solidified. Okay? And so, based on this evidence, people are saying that the rocks which were looked at today at various latitudes, which show evidence of glaciation, they were actually in the tropics 600 million years ago. So, here is an example from Australia where a lot of evidence came. Australia now, as you know, is at 20 south, but 600 million years ago, during the Marinovan period, these rocks were close to the equator at 10 north. Okay? So, these rocks show an evidence of glaciation. That means rocks close to the equator had ice sheets on top of them. Okay? And those ice sheets when they moved, they created evidence of glaciation. Okay? So, this is the evidence which was gathered over the last 60-70 years, which enabled us to believe that there was a snowball Earth. Okay? So, glaciological data has shown that two snowball Earths occurred in rapid succession and were unequal duration. The first one lasted 58 million years, the second one lasted only 15 million years. So, first of all, we do not know why the duration was so different and why these global glaciation occurred during this period. And there was a period of 10 million years when there was no ice at all, and then suddenly the planet went into snowball Earth. So, this is a puzzle which has been mostly resolved in the past 30 years. So, this is now the present picture, that there are only in the last 800 million years, we have evidence only for two periods, the Strutian and Marinovan, when ice is formed all the way from South Pole to North Pole, okay, all the way. So, that is a snowball Earth. Okay. But remember, this is evidence on the past. One has not been able to look at rocks on all parts of the earth. So, we cannot be 100% sure that ice covered every part of the earth. We can say with some confidence that ice covered most of the earth, 90–95%. 100% we cannot be sure, because for that we need more evidence. Okay. So, remember that when you come to discussion. And this also shows periods when there were mass extinctions, which we will not discuss in our course. And there are also periods when the ice came up to around 45 south. So, partly ice covered earth, that is not snowball, that is typical glacial period. Okay. And for example, Antarctica and so on had glaciers occasionally, and we have it now, but in between there was no evidence of ice. Now, the people who really discovered the fact that earth was once completely ice covered was the Caltech scientist Joseph Cruikshank, who is a biogeochemist, and Paul Hoffman, who is a geologist, who went to the field and looked for evidence. Okay. So, it was Cruikshank who argued that earth may have been covered with ice once upon a time, and Paul Hoffman went around the world looking for evidence that this really happened. Now, when this was first proposed, no one believed it, because it looked too far-fetched based on our present day earth. Okay. So, this was the hypothesis they proposed, that when most of the continents were around the equator, that is when the chances of earth temperature being low, because albedo of the earth will be higher. That is what they said caused the ice to cover the entire earth, and once ice covers the entire earth, the carbon dioxide cycle, by which carbon dioxide is converted to calcium carbonate and it comes back through the volcanoes, that cycle is stopped. Okay, because the earth is completely ice covered, there is no photosynthesis, so there is no possibility of a carbon cycle. So, what happens is, when the earth is completely ice covered, then volcanoes continue to erupt, because they are not dependent on temperature or other factors, they depend on plate tectonics, that is the movement of continents. So, as the volcano goes on erupting carbon dioxide to the, through the ice layer, the CO2 will go on building up, and there will come a point the CO2 is so high, the greenhouse effect is so powerful that it will start melting all the ice very quickly. Okay. So, this is the proposal they made, that earth gradually gets into the snowball state, remains there for some time, and then the carbon dioxide builds up because the carbon cycle has stopped, and all of a sudden all the ice melts for a very short period, and the earth becomes again free of the snowball state. Okay, and we will have ice only in the polar regions. Now, what you want to remember is that this is a very rare event. During most of the other periods, it is the carbon cycle of the earth, in which carbon dioxide is converted to calcium carbonate and it comes back as carbon dioxide to the volcano, that maintain the carbon dioxide amount at a reasonable level. So, that earth was largely ice free. Okay. So, you must remember that snowball is a very special occasion. It does not occur often, and earth being mostly ice free, not completely, is what has happened through the history of the earth. So, this is a pictorial indication of how we started from a polar covered ice, slowly the ice grows, reaches the equator, becomes a snowball, and then it comes out due to the greenhouse effect of carbon dioxide and becomes again ice free, and the ice again builds up. So, this is a cycle that was proposed by Cruikshank and Hoffman. Now, if you want to read about this in a simple way, I recommend strongly this book called Snowball Earth by Gabriel Walker, very nicely written book, non-technical, and it shows the story of this maverick scientist, which is Hoffman, and how he proposed this snowball Earth and how it was challenged and how he managed ultimately to convince most but not all scientists that Earth was once completely covered with snow. Okay, this is a very interesting story. You must read it to understand how science progresses in the real world. Okay. When a new hypothesis is proposed, a lot of people oppose it, and then the person who proposes has to go around finding evidence to show that he is right. As the evidence builds up, the hypothesis is accepted. You recall that Milankovitch proposed a theory of ice ages, which was not accepted, and only after he died, evidence emerged from the ice core in the polar regions that indeed Earth went through many ice ages during the last million years. So, this is how science progresses. It is good for everyone to understand how science works. So, science works by proposing new hypotheses, it is challenged by everyone, then you go around looking for new evidence to support a hypothesis, and until sufficient evidence builds up, the hypothesis is not accepted. Okay? That is how science operates. Now, the snowball hypothesis was accepted when a large amount of evidence was gathered by many scientists from various parts of the world, or evidence from rocks, showing that these rocks show evidence of glaciation, and that these rocks, which are now in Canada and in South Africa and Central Asia, were at the equatorial region a long time ago. Okay. So, you have to find rocks all over the world which show evidence of glaciation, and using paleomagnetic evidence demonstrate that those rocks were at or around the equator when they were formed. Okay. So, this is thing, but also remember this data is not perfect. You can see below the evidence of where the rock was in three categories. Big circle is very reliable, moderate circle not reliable, and a small circle is not so reliable. Remember that paleomagnetic evidence is not perfect. There are errors, like we saw errors in the ice age series when we are not sure exactly when that deposit was formed. Similarly, in the paleomagnetic evidence also there are errors, and so not all evidence is perfect. Some evidence is very good, some are not so good. You have to very carefully combine them. But I want to realize that there are 50 to 100 samples of rocks from all over the world which indicate that these rocks were affected by glaciers and they were around the equator. Especially you can see these red dots, which are the ones which are close to the equator. So, based on this, what is the evidence they had? The evidence was what is called striations, that is, when glaciers move, they carry with them a lot of broken rocks and rubbish, and they actually scrape the rock at the bottom of the glacier. These are called striations. You can see them, and if any of you have gone to the Himalayas and looked around the rocks, you will see evidence of striations. Okay? And the second is, as you look at these rocks, suddenly you will find rocks which are very different in character in the middle of a bunch of rocks which are of more recent origin. These are called drop stones, that is, stones which are dropped by glacier into some other location where it did not belong. Okay? So, these are the evidences that geologists use to identify glaciation. So, there are 48 places where signature obtained. This is the evidence of these striations, these scratches on the rock. So, next time you go to the mountains, Himalayas, look around. Many people go around to these places, but they do not really see interesting evidence just around them on the rocks. Okay. The two evidence, one of course is these striations, this scraping. The second is that it also polishes the rock, because when glaciers are moving slowly, they do scrape on the rock, but when there are very fine particles of dust or something, they will actually polish the rock. The rock looks very, very polished as well as scrape. So, in between you will see polish and then you will see the scraping. So, we have now lot of evidence independent. The glaciers are present near the equator or at low altitudes. Okay. And in these sediments, they also see the isotope of carbon 13 isotope showed a very low value, which is an indicator that photosynthesis was not there at that time. Okay. So, you have two evidence. One, there was glaciation in the tropics near the equator, and secondly, based on the carbon isotope evidence that the photosynthesis had reduced or almost stopped, which you expect if it is an ice covered earth. And lastly, there are banded iron deposits in the ocean sediments. Now, what are these? Now, you must remember that the earth contains a lot of iron. Okay? But when there is a lot of oxygen on earth, and if this iron is exposed to oxygen either in the atmosphere or even in the ocean, because if atmosphere contains a lot of oxygen, that oxygen is also dissolved in the ocean. Okay? So, there is enough oxygen in the ocean, then that iron will get oxidized to hematite, which is very red in color. Okay? So, if occasionally the earth is completely covered with snow and ice, then this oxidation cannot occur. Okay? So, when oxidation stops, you get a different kind of iron oxide, it has a different color. So, the color keeps changing in time. Occasionally we have hematite with very red in color and some other iron oxide which is somewhat black in color. You will see evidence of that in the next few slides. Okay? So, what you must remember is that three independent evidence showed us that earth was probably completely ice covered. One is glaciers near the equator at the ground level, not on top of the mountains. Secondly, the carbon isotope evidence showing low photosynthesis or no photosynthesis, and lastly the banded iron formation showing that iron oxide was not forming at that time. So, in anaerobic condition without oxygen, the stable chemical form of iron is iron ion 2 plus that dissolves in water. Okay? But when it reacts with oxygen, it becomes Fe3 plus, which is precipitated out as hematite. Okay? So, banded iron formation formed when oxygen first started building up 2 billion years ago, but not since then, because there is only one kind of oxygen, hematite. But 600 million years ago, suddenly this oxide stopped forming. So, he saw alternate layers of high oxide, low oxide. Okay? This is from the book called The Carbon Cycle by David Archer. It is a very nice book which I recommend. So, this banded iron formation in deep water are never found in very old rocks, because there was no oxygen at that time. Okay? So, these hematites which form when there is oxygen, Fe2O3, occur due to oxidation of iron after it is deposited. So, modern seawater contains less than 1 part per billion iron because iron is mostly oxidized. Okay. Joseph Crispin, whom we mentioned, argued that the presence of banded iron formation indicates there was a time when Earth's atmosphere had less oxygen or ocean was covered with ice. Of course, Earth had less oxygen if you go beyond 2 billion years, but after 2 billion years oxygen started accumulating in the Earth due to photosynthesis, and so during the last billion years oxygen was there. If the oxygen was there, then you should get banded iron formation. Okay? You should get only one kind of iron. Since he saw banded iron formation, he argued that Earth was covered with ice, but nobody accepted that hypothesis. Now, the evidence of banded iron formation is seen only during certain periods, okay, in the Earth, this one. So, it was formed, you can see the amount here in the last period when oxygen started forming, but in the last billion years in which we have more data, the only time it formed is in this period where we believe there was snowball Earth. Okay. Now, the oxygen content of the Earth has varied through time. You look at the last billion years, there was hardly any oxygen on Earth. Then after photosynthesis and various other factors, it started increasing. It went through a high and then it started declining, and again it oscillated. And but in the recent years, it is around, all of you know, 21%. Okay. But it was not so in the past. In the past it fluctuated a lot depending on photosynthesis and other factors. So our interest is in the last 600 million years, where oxygen has gone up to 35 and gone as low as 15, but most of the time is around 21%. But remember, this is not perfect, depends on a model, because to infer oxygen level in the past is not easy. You have to do indirectly. So there are 2 or 3 models, and you can see there are 2 different models which don't quite agree, but they all agree that there is no oxygen more than 2 billion years ago. It built up slowly and then rapidly. Okay. And we are concerned about the last billion years, where plenty of oxygen was there. So we expect all the iron to be hematite, but it was not so during this snowball episode. Okay. Here is an example of banded iron formation through history. When there was no oxygen, there was plenty of banded iron formed. Then once oxygen came, we had only one kind of iron, that is hematite. Then again it showed a little bump in this period where snowball occurred, and it went back to hematite later. So what I want to talk to you is now is in words here, so that you can fully understand. You can read it in leisure to understand how this banded iron formation occurs, under what conditions. Now here is a picture of the banded iron formation, not there in the first 2 billion years of Earth. Once oxygen came, the oxide started forming, and then it declined, and then it came again. So we are focusing on this period where we have banded iron, and we want to know, is this on account of snowball Earth. Here is a picture of the banded iron. Okay. You can see the color changing quite rapidly. Okay. Bright red of hematite, then some other oxide which doesn't have that color, then back to, and so on. So these were the first evidence for Joseph Crispin to say that something happened. And then this layer, see, there is a banded iron formation here, a banded iron. In between, you see there is no banded iron, and these rocks are very different from rocks here and here. Okay. These are calcium carbonates which contain this iron oxide. So this is called drop stone. These are rocks of a different kind which were deposited on top of this rock, and then more deposit occurred above. Okay. So, this is in Canada, which is where Hoffman first looked at this and was puzzled. Okay. So, this was the first interesting evidence of a lot of banded iron, no banded iron, but evidence of glaciation, and then banded iron. Okay. So, the argument is that when Earth does not contain much ice sheet, the ocean contains lots of oxygen. So, Fe3 plus is preferred, and you get one kind of iron oxide. When Earth is completely covered with ice sheet, you get Fe2 plus, okay, because of reduced oxygen in the ocean, and you get a different kind of iron oxide. So, when you see alternate layers of these iron oxide layers, you must assume that Earth was covered with the ice sheet and then it was uncovered, so it alternated. Okay. So, this is from Hoffman's website. So, let me summarize what we have learned today. The assumption that Earth completely covered the ice is called hard snowball. Okay. There are people who believe it may not have occurred because the evidence is not perfect. There are some who believe in soft snowball or slush ball, where ice covered most of the Earth except very close to the equator. There was an area where there was no snow, so that life could survive. Now, this is a thing that many biologists believe in, because they can't believe that Earth was completely covered with snow, then life would be gone. So, they wanted some region, very small region, in which life would survive for some time until the snowball ended. Okay. So, we do not worry about it hard or soft. We go by glacial deposits at low latitude, which plenty are there. Then on top of that, there are calcium carbonate layers, huge layers, when the snowball ended and Earth had a very strong greenhouse effect. And then again it reappeared, the banded iron formation, and isotopy evidence from carbon 13 of very high CO2 after deglaciation. All these evidence, but of course, whether it is hard or soft snowball is not so easy to convince. Okay, we will continue this issue in the next lecture.